Hello, everyone. We are going to continue on with Chapter 2 homework. We left off on question 5. I will go ahead and show you that. Let me show you that here. Screen 2. So you can see we left off on question 5. We're going to go on to question 6. We'll finish this homework setup. Let me pull up question. Go ahead and do that. Resources. Just give me a second. I'm going to stop sharing. I'm going to pause. All right, I'm resuming recording. Let me go ahead and share my screen. I have it loaded up now. We left off on question 5. We were able to answer question 5. Question 6 is pretty similar. Let me get my pen out and show you to you. So with question 6, it says, the skeletal structure and line angle mode of 2 isopropyl toluene, and we'll go over that, is shown. Identify the number of hydrogen atoms bound to each carbon atom in the structure. So I'm going to go to the next slide here on my pen. So on question 6. So let's go ahead and draw the structure. So we have this. I'm going to draw the double lines. Usually I just make it a circle, but we'll go ahead and draw the lines like that. And I just want to make sure that I have everything in here. And it gives a name of 2 isopropyl toluene. So, here's your 1, here's a 2 position. So the toluene is this right here. So at the 2 position, we have an isopropyl group, and you can see that right there. So that's how you go about that. And then how many hydrogens? Well, you're going to have 1 here, 1 here, 1 here, 1 here. There's going to be no hydrogens there. You're going to have 3 hydrogens here, and I'm going to go ahead and draw them all in. You're going to have 0 here. I'm going to get rid of this. Some people may confuse that with 2 hydrogens, so I don't want to do that. This is just the 2 position right here. And that's because you have this isopropyl group coming off. And right here, you're going to have 1 hydrogen here, and you're going to have 3 hydrogens on the end. So this question wasn't too bad. And none of them have 4 hydrogens. So if you select that, please do not select the 4. So that's question 6. Question 7. It says label the functional groups in the molecule. So in chapter 2, we went over functional groups. And here we get to practice the functional group. So it would be a good idea if you pull out the chapter 2 and that PowerPoint slide that we went over on the functional groups. This would be a good time to pull that out. If you have it printed off, that'd even be good. That'd be great too. A lot of times when I'm taking my classes, I'm taking MBA 875. I print off the documents myself, and I just go over them. So that's just a helpful hint or suggestion. So I'm just going to draw out the structure here. Sometimes this is the longest part of it, but I do really like this XP pen over the chalkboard or whiteboard, only because it gives you a lot more ability for creativity. You can erase a lot quicker. We can do these recorded sessions. Did I go? Yeah, I did that. See right there, I made a mistake, but that's okay. Look how quick I was able to delete that. This is H2. So do I have everything? I think I do. So here we have the alkoxy group. Like I said, it'd be a really good opportunity to pull out that table that we went over for chapter 2. That way, that gives you a really good idea of what we're doing. And maybe I'll even show it to you. Let me pull up the PowerPoint slide. I won't be able to look at them both at the same time. Pulling up the slide right now. Just give me a second. When you want something really quick, sometimes it doesn't happen as quick as you want it to happen. No. Here we go. I found it. It's pretty early on. So it's on slide 17 and 18. I'll go ahead and share that screen with you. So slide 17 and 18, if you have this printed off, that's a really good idea. That way you get a really good look at, what we're looking at. So I would highly suggest to print this off, and then, it'll make it as you're first going through. You want to look at the group, and you want to look at it at the same time. If you've done this many times before, like myself, it is even helpful, for myself too, but especially for beginners. So why don't we go back to the homework? I want to make sure I'm on the homework. So we're on the homework. So we have a hydroxy group. So this alkoxy group, that's because you have this some type of methyl propyl, you have some type of carbon chain coming off. That's how you get the alkoxy. So this is going to be your hydroxy group right here. That's because you have an OH. So you'll have a hydroxy group. Then we're going to have amino. That's NH2. For halo, that would be like Cl, Br, I, F. So these would be your halo group. Have your another amino group. And you have your bromine group. It's not bromine group, halo group. Sorry about that. And that's it. So I'm going to stop sharing real quick. I'm going to pause the video and I'm going to come back. Just give me 1 second. All right, we're back on question 7. So you should be, I think that's it for question 7. And there was 1, 2, 3. There were 6 groups for question 7. We labeled all 6. We labeled all 6 right there. So let's go on to question 8. And if you're watching this, you can just pause, go back, fast forward. So question 8, it says an unknown compound was found to have the molecular formula C5H12O2. And that noise that you hear in the background is a guinea pig. I apologize about that. To which compound classes could the compound belong? And check all that apply. So, some possible functional groups. Let me see. Possible functional groups would be an ether and an alcohol. And that was question 8. So let's go to question 9. Question 9 says the structures shown are missing lone pairs. Complete these structures by adding electron dots as needed. So we'll go ahead and draw A with some type of thiol compound with the sulfur. This sulfur is right below oxygen. So you're going to have 2 lone pairs like that. Again, you're going to put them like that. You can think of water having 2 lone pairs right here. So it's going to be kind of similar. So let's see. So for B, we have this group right here. NH2. And you know, remember for ammonia, we're going to have 2 pairs right here. So we're going to draw that right there. And for oxygen, you're going to have these 2. So make sure you get these pairs right there. So that's A and B. We'll go to question 10. Question 10 says, consider the resonance structures of formate. Select the true statements about the resonance structure. So they provide you the resonance structures. There's going to be 4 choices. You're going to select these ones. The second one says each carbon-oxygen bond is somewhere between a single and a double bond. And that's true because you have resonance right here. So that's why this one's true. And the actual structure of formate is an average of the 2 resonance form, and that is again true. So we did 10. Let's go on to 11. So 11 says, consider the incomplete structure shown. Draw an alternative Lewis structure for the incomplete structure. Show the unshared pairs of electrons and non-zero formal charges in your structure. Don't use radicals. So it says don't use radicals. So they give us this incomplete structure and they want us to draw an alternative one. So the alternative would be to, I'll show it to you. You know, you have this right here. You're going to jump these electrons onto the bromine. So when we do that, we're going to have a positive charge now because, you know, carbon is supposed to be bonded to 4, and now it's only going to have 3. Here it's 4. Now it's only going to have 3. So it's going to have a positive charge because 4 minus 3 equals +1. And then that bromine is going to be neutral. 7 minus 7 equals 0. So the formal charge would be +1. All right. And if you have any questions, you can put them into the discussion board. I'd like to see some, you know, students put some questions in the discussion board. That way, you know, everyone gets to see, you know, what, because a lot of people may have the same questions. So question 12, it says a Lewis structure for the carbonate CO3 2- is shown, but is incomplete. Complete the structure by adding informal charges and non-bonding electrons and draw the other 2 major resonance structures that fit the octet rule. So we're going to draw it first right here. So we have the CO3 2-. We're going to put it right here. -1, -1. So the other 2 resonance structures would just be moving this double bond around. So I won't have that line. So, but we're going to have 2 more resonance structures. You're just going to move that double bond around. So in one instance, it's going to be here. In the other instance, it's going to be on the other side. So just making sure that I have all the electrons. That's going to be the most difficult thing. There we go. So that's question 12. Question 13. It says structure A, complete the structure by adding non-bonding electrons. So why don't we go ahead and do that? It's gonna be a -1 because 5 minus 6 equals -1. And then that's structure A. Structure B will be this right here. And which structure contributes most of the hybrid? Well, you want to put the one with the negative charge on the nitrogen because it's going to be the more electronegative atom. Sorry about that. Sometimes I get these spam calls. Electronegativity increases up and to the right. So the structure with the negative charge on nitrogen contributes more. So you have 3 options. You're going to select the middle one. The structure with the nitrogen. So you want the structure with a negative charge on the nitrogen. Negative charge on nitrogen. So let's go to 14. It says draw curved arrows to form structure B. So they show you structure A and structure B. We just have to draw curved arrows. So this is positive because it's 5 minus 1. So to get to the next structure in structure B, you just take these pair, put them here, and that's going to release this pair up here. Now they want you to, so this would be A and then B. We're going to take structure B. And we're going to turn that into structure A. So to do that, this lone pair, it doesn't have to be this lone pair. It could be on the left. You know, they're all equivalent. And this is going to come here like that. So that's what they wanted for 14. Uh, 15. And it says draw curved arrows to form the next most important resonance structure. For the enolate shown, should I show an enolate? Let me see. Okay. So there's 2 answers to this one. I'm going to kind of separate them apart. Here we have HC. This is negative because, you know, 4 minus 5 equals -1. So what's going to happen is you're going to put these right here, and these are going to come up on the oxygen. And once that happens, you're going to get a structure that looks like this. And to reform, to go back to this structure, all you're going to have to do is do their opposite. And that's what you do. So that was question 15. Question 16. It says draw 2 resonance structures of the cation shown, shifting only 1 electron pair in each step. Be sure to include the formal charge on structures B and C. Only move 1 double bond. Each resonance structure should contain only 1 charge, a positive charge. So let's see, we have 3 arrows, or not 3 arrows, but 3 answers. So 3 answers are looking for. So we have something that looks like this. Oh. So if we put the positive, so we can jump there's resonance right there. So then we'll form the same thing. Not the same thing, but we're just moving the double bond and the charge. So then we'd have that double bond right here. If we have the double bond right here, there's a positive charge right there. And we still have this. So then we're going to move it here, and that's going to move that positive charge right there. So I don't want to do that in case that confuses someone for the answer. But we'll show it right here. We have that positive charge that moved, you know, like I said, I'll put a star right here, but then it might confuse someone, so I don't want to do that. So we just moved the charge. And you could do the reverse to go back. Notice though that this double bond right here doesn't participate in the movement of that cation charge. Okay. Erase that. So that was 16. Let's go on to 17. The 17 says, identify the major and minor resonance contributor for the formate anion, HCO2 minus. Remember, you want to have, so the major contributor, you want to decrease formal charges, and you want to put the formal charges, and formal charges go on the more electronegative atom. And remember, electronegativity increases as you go up and to the right. Sorry about that. I have terrible allergies. So we're going to decrease that down arrow means decrease formal charges. So instead of having 2, it'd be better to have just 1. You know, the 1 would be better than to have two formal charges. So in A and B, you're going to select the major contributor is going to be A and B because you only have 1 formal charge and it's on the more electronegative atom. And identify the minor contributor, and that would be C. So the minor one, so this would be the major, and the minor would be C. And option D really doesn't exist. That's why we're not choosing that one. C puts the form, C, you can see we have 3 formal charges, right? There's 3 formal charges, but when you add them up, you know, you have -1 plus -1 plus 1, and that gets you, let me see, that gives you -1, but now we still have 3 versus there is only 1 formal charge over here. That's why it's a minor contributor. 18. They want us to draw the resonance structures. So we have we're gonna put the arrow like that. This would be a positive now because this would be 6 minus 5 equals +1. And here this will be a negative. And if you thought about this, this is going to be your minor. This is going to be your major contributor, resonance contributor. All right, so that was 18. Let's go to 19. It says a cationic intermediate for the electrophilic addition of chlorine to the para position. A phenol is shown. So let me go ahead and show you something. So, you know, I'm just going to draw an X, and this ortho, I'll draw it as a Z. So this would be ortho. This would be meta, and this would be para. So just keep this in mind. So it says account for the electrophilic addition of chlorine to draw the resonance structure as the major contributor, include all non-bonding electrons. So they show us this structure right here. Let me go ahead and show that to you. and we have to draw the major resonance contributor. So what we're going to do is these electrons are going to come here, and then these electrons are going to go here, and there's going to be, let me see, and that'll be the major contributor. So why don't we go ahead and draw that. So we got that 6-membered ring, got the 2 double bonds, we got the here, positive charge is here, and chlorine is here. So that'd be the major contributor. That's 19. And then 20. It says the structure, let me see. It's loading up on mine. The structure is an anion with 3 possible resonance contributors. So it wants us to draw some structures right here. So let's go ahead and do that. So we'll do for structure, there's four answers here. So answer 1, be negative. I'm going to draw that one a little bit that way it doesn't confuse anybody. There's a positive charge here, negative, negative. So I have that right. So structure 2. This. I think I got everything. And finish with the resonance structure for 3. And we're just moving around, electrons. All we did was take these electrons on the sulfur, put them between the sulfur and nitrogen. That may force the double bond to become a single bond from the nitrogen and oxygen, and put the electrons on the oxygen. And we'll draw resonance structure 3. So it says which one is the most stable. So most stable. Oh, sorry about that. Some reason it's not 1 to write. Most stable. Let's look at the options. There's 4 options. You're going to select this one. And that's the one with the structure with a positive charge on the nitrogen, positive charge on nitrogen, and negative charges on sulfur and oxygen. And that would be, let me see, this structure right here. All right. I think that's it. So that's it for question 20. So we are done with chapter 2 homework. I was going to share something that I shared with my previous classes. It's going over naming. So just give me a second to pull that up. I'm going to pause the video. So what you're going to see, I used to teach out of the Carty book, and I thought Carty actually had a really good section on naming. That's why I wanted to include it for you. So this lecture is, just includes the naming part that we're going to go over right now, and the homework from chapter 2. So I'm going to go ahead and start sharing my screen. You'll see why I really like this this inner chapter A from Carty. We've already started going into a lot of the naming in the Klein book, but they haven't really gone over really how to name compounds. And I think that's really necessary at this point in time. If they're expecting you to know how to, to to look at compounds for naming, you should have like just a basic introduction for naming compounds. And that's what this does right here. And in the Carty book, they had like, they have 20 something chapters, but between chapters, they'll have these inner chapters. So that's why they call it inner chapter A. So it's really a chapter, but they just call it inner chapter A. So let me get my pen out. And this is provided in the document, so please go ahead and look at it. I don't want the laser point. Sorry about that. I'm gonna have to enable editing for me to write on here. All right. So, why would you want to learn how to name organic compounds? Because there's millions of organic compounds, and there just has to be some type of set way of going about naming compounds. That way scientists can, when they talk about a name, everyone's talking about the same compound. Otherwise we could have, just for instance, I'll just give you an example. This is a made up example. We could have 4 carbon compound, 1, 2, 3, 4. This is butane, but let's just say someone in a different area, it doesn't have to be a different country, just a different institution wanted to call this, I don't know, butane. This is just, for example, why we have a common naming system, nomenclature. So IUPAC was founded in 1919 to provide a standard for naming inorganic. That's compounds really that are the transition metals, non-carbon and organic, and these ones are containing carbon. So alkanes tend to be the simplest molecules to name under the IUPAC system. They're your single bonds. Alkanes contain only carbon-carbon and carbon-hydrogen single bonds. They contain no functional groups. The most basic alkanes are the straight chain. You can see how I drew my little straight chain alkane up there, or linear alkanes. So all straight chain alkanes have the suffix ane and the prefix meth, eth, prop, but, and we're going to go over on that on the next slide. So it's a really good idea for you to learn these suffixes. Here, methane has 1 carbon, ethane has 2 carbon, propane has 3, butane has 4, pentane has 5, 6, 7, 8, 9, 10. I'll be honest with you, and I don't want this to be you. I want you to be the ones that said, okay, Dr. Buston is the one that taught me organic chemistry, and I know my naming. I've had some graduate students actually, confuse hexane and heptane, or propane and butane. So I don't want that to be you. I want you to be the ones, telling or letting the students in your classes know that you know how to name compounds. So if a hydrogen atom of an alkane is replaced by another atom or a group of atoms, we say that the alkane is substituted. So here, this could be OH, could be SH. It's just a substituted. So you can have multiple substituents on a molecule. The halo substituents are F are fluorine, chlorine, bromine, and iodine. So fluoro, chloro, bromo, and iodo. If it has an NO2, that's a nitro group. And they give you some, I don't want to read to you all this, but I think you should go through and read that to yourself though. And that really kind of gives you an idea of, how to name a straight chain alkane. Here we see this as 1-chloropropane. Why is this propane? It's a 3-carbon system. And at the 1 position, we have a chlorine. Here we have 2-chloropropane. We have 3 carbons. And at the 2 position, we have a chlorine. So, establishing the number system for a main chain that has 2 or more substituents, it says choose C1 so that the substituent that is counted first has the lowest locator number. And you saw this right here. So we have a 1 right here. Let's just say, for instance, we started here at 1, 2, 3. Well, this is the same thing as this right here. We just flipped it. So that's why we started at 1. Because you could have went 1, 2, 3, but you always want to start with the lowest number, 1. If each choice for C1 results in a tie for the locator number of the first substituent, then C1 is chosen so that the second substituent encounter has the lowest locator number. And this goes through some tiebreakers right here. So this would be the correct numbering. Numbering starts from the left to give the first substituent the lowest locator number. So this is the first substituent encountered. Remember, we could have started on this side. Remember, I made that mistake in a previous lecture, but I quickly caught myself because if you recall, that homework question had it, I think it was a hexane that had a couple double bonds, and I started over here, but then I realized, well, I don't want to put the double bond, and it was over here. I don't want to put the double bond in the 2 position. I want to put it in the 1 position. So it's the same thing right here. We can get it at the 2 position, so that would be the correct way. Adding prefixes when the main chain has 2 or more substituents. Remember, we had something that had, let's just say we had, you know, I have butane and I have two carbons coming off. So this would be 2-diethyl or dimethyl. Sorry about that. 2-dimethyl butane. So we have a methyl, ethyl, propyl, butyl, pentyl, and hexyl. And I think this is really good for you to actually memorize. Di, tri, tetra, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9. Because if you're studying for medical school or dental school or PA school or any type of professional school, they're going to expect you to know this on whatever professional exam that you take. So we have the straight chains right here. So here we have 3-methyl hexane. So in the 1, 2, 3, 4, 5, 6, that's how you get the hexane. At the 3 position, we have a methyl group. So here we have octane, so that's 8. At the 5 position, we have a propyl group. A propyl group is 3 carbons. And at the 4 position, we have dichloro. So di means 2. The way in which a molecule is drawn can influence your perception. Count the carbons to find the longest possible chain. So this is the incorrect. Because this is pentane. Oh, for some reason it's not writing. Let me. Oh, I don't know why it's not writing for. Let me see. Here we go. So 5 versus 6. So we want to be 6 because that's a longer chain. Here we have pentane. Here we have butane. Butane's 4. Pentane is 5. So think about it before you name it butane or pentane. Which one is the longest chain? Yeah, we can go 4 this way, but if you start up here, you have 1, 2, 3, 4, 5. You get a 5-carbon chain versus a 4-carbon chain. So not all alkyl groups are straight chain alkyl groups. An alkyl group can also be branched, having more than 1 terminal carbon, and they give you some helpful advice and tips right there. So if a molecule contains at least 1 ring made entirely of carbon atoms, a ring can act as the root of the molecule as a cycloalkane. So cyclo means a ring structure. So I drew a circle for a ring. So here we have 3, 4, 5, 6, 7, and 8. This is going to be the most stable ring, and this is going to be the most strained ring. And the release of strain continues this way, and this is the most stable, and then strain continues again that way. Alternatively, the rings could be treated as substituents called cycloalkyl groups. And what does that mean? Let's just say we have some long chain carbon, and then I have some group like that coming off. So at the 2 position, we'd have a cyclopropyl group. Here they're showing at the 2 position, you have a cyclopentyl group. 3 position, you have a methyl group. So it's 2-cyclopentyl, 3-methyl octane. Here at the 1 position, we have 1-methyl hexyl cyclooctane. So the longest continuous chain has 7 carbons. So let me count that 1, 2, 3, 4, 5, 6, 7. One, 2, 3, 4, 5, 6, 7. Yep. If it's a 7 position, I think they made a mistake. It should be, instead of hexyl, it should be hepsyl. So that would say typo on their part. Because hex is 6, HEP would be 7. So you wouldn't start it right there. I apologize for that. This would be, unless, sorry about that. Here's a 1, 2, 3, 4, 5. I confused myself. So this is a 6-carbon chain right here. At the 1 position, you have a methyl group. And at the 1 position, you have a cyclooctane group. So that's how you get the hexyl group right here. So if a molecule's root is cycloalkane, we establish a numbering system just as we would with linear alkanes. So C1 has the greatest number of attached substituents. They're saying that would be C1. Numbering increases clockwise or counterclockwise around in the ring so that the next substituent is counted earliest. So 2, 3, so we do go at 3, 4. So that's why you go this way, just following the rules. We had the most here. The next one here, because if think about this, if we went around clockwise, we wouldn't hit the first one till 4, but 3 is less than 4, so that's why we go that way. So it's 3 bromo, 4 chloral, 1 dimethylhexane. So an ether functional group can be represented as ROR, and we saw this in our chapter 2. And here's your ether group. Naming an ether. This would be dimethyl ether. There's 2 methyl groups. Diethyl, there's 2. See that? There's two, and ethyl means 2 carbons. Di means 2, methyl means 1 carbon. Oh, and propoxy cyclohexane. So here's your propoxy group. Here's some other examples. Methylpropyl ether. Here's your methyl group. Here's your propyl group right here, and it's an ether because ROR. And they give you some other examples. So sometimes you'll see trivial names, and sometimes you'll see common names, and they've been integrated into the nomenclature. So the IUPAC name would be butane. N-butane stands for normal. This is isobutane. Here's 1, 2, 3, 4, or you could call this methylpropane because propane is 3, and at the 2 position there'd be a methyl group. Here's pentane or normal pentane, and they give you some other examples. And here's some other examples of trivial and IUPAC names. So a primary carbon, I talked about this a little bit today. A primary carbon is directly bonded to one other carbon atom. So here we have a primary carbon. Secondary carbon, you're attached to 2 other carbons. So here we have 1, 2, and 1, 2, so it'd be your secondary. Your tertiary carbon is going to be attached to 3, 1, 2, 3, and your quaternary carbon will be attached to 4. So you have 1, and let's draw that out for you. 1, 2, 3, 4. So you have a secondary carbon and a tertiary carbon right here. So you have trivial names for alkyl halides. So again, you have the trivial name and the IUPAC name. Trivial names for ethers. And here are some summary and conclusions. So basic alkanes are the straight chain alkanes. If a hydrogen atom of an alkane is replaced by another atom, remember if this hydrogen, that's not a good place to put that. If this hydrogen now is a chlorine, it has a substituent on there, has a halo group, and numbers are used to locate substituents along the main chain or ring. Here are some more conclusions and summary. I'll let you go through and read that on your own. And they end it with some more summary and conclusions that we went over. But if you have any questions on how to name, I think that's it. Please let me know. Remember, the primary carbon only has only has 1 carbon attached. Secondary would have 2, tertiary would have 3, and quaternary would have 4. And I think a really good example, it's not letting me erase, a really good example of that would be this right here. This group right here gives you a really good example of looking at primary, secondary, tertiary, and quaternary. So that's all I have today. Let me know how you like the lecture. So just go ahead and put it in the chat board. And I will see everyone on Thursday. So, I look forward to getting back with you. I had a family emergency I had to go attend to. That's why I'm posting this lecture a little early. So thank you.